24 million years ago, a formidable predator ruled the ancient oceans. This creature wasn't a shark or a whale, but a colossal dolphin known as Ankylorhiza. At 16 feet long, with a skull built for ramming and teeth designed for shredding, this ancient cetacean dominated the seas. Its existence raises intriguing questions about the evolution of marine life and the forces that shape our planet's ecosystems. During the Oligocene epoch, dolphins were far from the playful, intelligent creatures we know today. Ankylorhiza, the largest toothed whale of its time, represented a different kind of cetacean, one that inspired fear in its prey and played a crucial role in shaping marine food chains. Its reign as an apex predator offers a fascinating glimpse into a world vastly different from our own. The story of Ankylorhiza is a tale of evolutionary success and eventual decline. By examining this ancient predator's rise to power, we can gain valuable insights into the dynamic nature of life on Earth and the constant changes occurring in our oceans. What factors contributed to Ankylorhiza's dominance, and what can its existence teach us about the ongoing evolution of marine mammals? Ankylorhiza dominated the ancient seas for over 6 million years, from 29 to 23 million years ago. Its reign was the result of millions of years of precise evolutionary refinement. The fossilized bones of this ancient beast hold a shocking revelation about the nature of dolphin evolution, changing our understanding of life in Earth's prehistoric oceans. The emergence of Ankylorhiza marked a pivotal moment in cetacean evolution. This formidable predator appeared shortly after the divergence of toothed whales from baleen whales, which occurred around 35 to 36 million years ago during the Oligocene epoch. As Dr. Robert Busenecker noted, what makes that important is its evolutionary position as a very early branching dolphin. This positioning provides crucial insights into the development of features we see in modern dolphins and other cetaceans. Ankylorhiza's success can be attributed to its unique adaptations for power and speed. Its robust skull structure contributed to a significant bite force, while its teeth were designed for efficient predation. These teeth featured longitudinal ridges that enhanced the creature's ability to cut through flesh, making it a formidable hunter in the ancient seas. Interestingly, Ankylorhiza's forelimb morphology was intermediate between stem cetaceans and modern taxa, highlighting its unique evolutionary position. The nearly complete skeleton of Ankylorhiza, discovered in the 1990s during excavations in South Carolina, provides unprecedented insights into the evolution of swimming adaptations in toothed whales. This remarkable find includes a well-preserved skull, most of the vertebral column, rib cage, and one flipper. The skeleton reveals both primitive features and adaptations for faster swimming, including a flexible lumbar region and a narrowing of the tailstock. These characteristics allowed Ankylorhiza to move through the water with greater efficiency and agility than its contemporaries. To put Ankylorhiza's size into perspective, it measured approximately 16 feet in length. This made it larger than most modern marine predators, including the great white shark, which typically reaches lengths of 13 to 16 feet. Ankylorhiza's impressive size, combined with its powerful bite and efficient swimming abilities, placed it at the top of the marine food chain during its time. The story of Ankylorhiza's discovery is almost as fascinating as the creature itself. The first fossil, a fragmentary skull, was found in the 1880s during dredging of South Carolina's Wando River. However, it wasn't until the discovery of the nearly complete skeleton in the 1990s that scientists could truly begin to understand this ancient predator. This skeleton was uncovered during construction work in South Carolina by commercial paleontologist Mark Havenstein, highlighting the importance of ongoing excavation and research in our understanding of prehistoric life. Reconstructing Ankylorhiza's appearance has been a complex process, involving careful analysis of its fossilized remains. Scientists have pieced together an image of a streamlined, powerful creature with a robust skull and a body built for speed and agility in the water. Its teeth, adapted for shearing through prey, paint a picture of a fearsome predator that likely struck terror into the hearts of its contemporaries. Interestingly, Ankylorhiza's classification history includes an initial misidentification. It was originally classified as a member of the genus Squalodon, a mistake that persisted until recent discoveries clarified its status as a distinct genus within the Odontocetes, or toothed whales. This reclassification underscores the ongoing nature of paleontological research and the importance of new discoveries in refining our understanding of prehistoric life. The significance of Ankylorhiza in understanding cetacean evolution cannot be overstated. Recent studies have highlighted that Ankylorhiza's adaptations for swimming and predation evolved independently from those of baleen whales, suggesting convergent evolution in locomotor features. This revelation sheds new light on the complex evolutionary pathways that led to the diverse array of cetaceans we see today. Ankylorhiza's evolutionary adaptations showcased a formidable predatory arsenal that would impress even modern marine hunters. This ancient cetacean's unique skull structure and teeth arrangement played crucial roles in its dominance of ancient oceans. At the heart of Ankylorhiza's predatory prowess was its formidable skull. Making up approximately 20% of its total body length, this robust cranial structure was a key factor in its hunting success. The skull featured the largest temporal fossa of any known toothed whale, a characteristic directly linked to its impressive bite force. This expansive area provided ample space for muscle attachment, allowing Ankylorhiza to generate tremendous power when clamping down on its prey. Ankylorhiza's dental arsenal was equally impressive. Its teeth were specially adapted for a unique hunting strategy, ramming. The incisors protruded forward like tusks, enabling Ankylorhiza to inflict severe damage on its prey without necessarily biting. This adaptation allowed for a more versatile hunting approach, combining the benefits of ramming with the option for a powerful bite when needed. The combination of Ankylorhiza's skull structure and tooth arrangement created a predatory package that was both versatile and deadly. Its ability to ram prey with its tusk-like incisors, followed by a bone-crushing bite, made it a formidable hunter in the ancient seas. This hunting strategy bears some resemblance to the techniques used by modern killer whales, which are known to ram and stun their prey before delivering a fatal bite. Ankylorhiza's neck was another key component of its predatory arsenal. Unlike many modern cetaceans, Ankylorhiza possessed a highly flexible neck, enhancing its ability to maneuver and bite vulnerable parts of its prey. This flexibility, combined with its powerful jaws and specialized teeth, allowed Ankylorhiza to target specific areas on its victims, maximizing the effectiveness of each attack. The biomechanics of Ankylorhiza's ramming capability suggest it could inflict catastrophic damage on its prey. The force generated by its streamlined body, propelled by powerful muscles, would have been devastating when concentrated on the point of its protruding incisors. This ramming ability, coupled with its agility and bite force, made Ankylorhiza a terrifying predator in its marine ecosystem. Ankylorhiza's hunting prowess wasn't limited to its physical attributes alone. Its body design was optimized for fast swimming, allowing it to chase down and kill large-bodied prey, including other cetaceans and marine reptiles. Notably, Ankylorhiza was the first known echolocating whale to become an apex predator, showcasing advanced sensory capabilities that further enhanced its hunting efficiency. This combination of speed, power, specialized weaponry, and advanced sensory abilities made Ankylorhiza a top predator in its time, capable of dominating a wide range of marine environments. While direct evidence of Ankylorhiza's prey interactions is limited in the fossil record, its anatomical features provide strong clues about its hunting behavior. The wear patterns on its teeth, the structure of its skull, and the adaptations for speed all point to a predator that was well equipped to take on large, fast-moving prey. It's likely that Ankylorhiza occupied a similar ecological niche to that of modern killer whales, preying on a variety of large marine animals. The Oligocene marine environment of South Carolina, where Ankylorhiza lived exclusively, was a vibrant ecosystem teeming with diverse life forms. This rich habitat provided an abundance of prey species, supporting the existence of such a formidable apex predator. The ancient waters were home to a variety of creatures, including prehistoric seals, devil rays, stingrays, cow-nosed rays, wedge fish, and sea turtles. The shark population was particularly diverse, with over 10 different species inhabiting these waters, ranging from nurse sharks and hammerhead sharks to thresher sharks and megatooth sharks. Ankylorhiza's role as the apex predator in this ecosystem was pivotal. Its presence likely had far-reaching effects on the entire food chain, influencing the behavior and evolution of its prey species. The pressure exerted by such a dominant hunter would have driven adaptations in smaller marine animals, potentially leading to changes in their defensive strategies, reproductive patterns, and even physical characteristics. However, Ankylorhiza wasn't the only large predator in these ancient seas. It coexisted with various species of dolphins and whales, including Squalodon, which would later fill the ecological niche left by Ankylorhiza after its extinction. This suggests a complex web of predator-prey relationships and potential competition for resources among these large marine mammals. The hunting strategies employed by Ankylorhiza remain a subject of scientific speculation. While direct evidence is scarce, insights can be drawn from studying modern cetaceans, particularly killer whales. These contemporary predators are known for their sophisticated pack hunting strategies, involving coordinated efforts to capture prey. It's possible that Ankylorhiza exhibited similar social behaviors, potentially hunting in groups to take down larger or more challenging prey. Ankylorhiza's impressive individual adaptations for predation, including its powerful jaws and ramming capability, suggest it was also a formidable solo hunter. Its ability to pursue and overpower large prey on its own would have given it a significant advantage in the marine ecosystem. This dual capability, potentially hunting both alone and in groups, would have made Ankylorhiza an exceptionally versatile and successful predator. The relationship between Ankylorhiza and smaller dolphin species of its time is another intriguing aspect of its ecological role. As the largest toothed whale of its era, Ankylorhiza likely dominated these smaller relatives. This dominance could have manifested in various ways, from competition for prey to potential predation on smaller cetaceans. The pressure exerted by Ankylorhiza may have influenced the evolution and behavior of these smaller dolphin species, possibly driving them to occupy different ecological niches or develop new survival strategies. Ankylorhiza's impact on its environment extended beyond its role as a predator. As a large, active marine mammal, it would have played a significant part in nutrient cycling within the ocean ecosystem. The movement of these creatures through different depths and regions would have contributed to the distribution of nutrients, indirectly affecting the entire marine food web. The social behavior of Ankylorhiza, while not directly observable, can be theorized based on what we know about modern dolphins. Many contemporary dolphin species exhibit complex social structures, engaging in cooperative hunting, communal care of young, and sophisticated communication. If Ankylorhiza shared these traits, it would have been a physically powerful, socially and cognitively advanced creature for its time. Ankylorhiza's physical adaptations were truly remarkable, holding clues to the future of all whales and dolphins. This prehistoric hunter's anatomy tells a story of convergent evolution that would leave its mark on the seas for eons. Ankylorhiza's role in cetacean evolution was pivotal, serving as a crucial stepping stone between early whales and modern dolphins. Its unique blend of primitive and advanced features provides a window into the evolutionary process that shaped today's marine mammals. For instance, Ankylorhiza's flexible neck and streamlined body represent a balance between size and agility that would become characteristic of many marine predators. This ancient cetacean's presence in the ecosystem likely triggered a cascade of adaptations in prey species. As Ankylorhiza honed its hunting skills, potential victims would have been under intense pressure to develop counter-strategies. This could have led to faster swimming speeds, improved camouflage, or even changes in behavior such as increased group sizes for protection. The evolutionary arms race between predator and prey would have driven rapid changes in both parties. One of the most fascinating aspects of Ankylorhiza's anatomy is its demonstration of convergent evolution with modern whales. Despite evolving independently, both toothed whales and baleen whales developed similar adaptations for efficient swimming. These include a narrowing of the tailstock and a shortening of the humerus in the flipper. This convergence highlights the strong selective pressures present in the marine environment, shaping diverse lineages towards similar solutions. Ankylorhiza wasn't alone in its role as an ancient macropredatory whale. Other extinct species like Basilosaurus and Leviathan also occupied similar ecological niches. However, Ankylorhiza's unique combination of features sets it apart. Its ramming capability, coupled with a powerful bite force, suggests a hunting strategy that was both versatile and effective. The evolutionary pressures driving Ankylorhiza's specializations were likely multifaceted. The need for efficient propulsion in water led to its streamlined body shape and powerful tail. The abundance of large prey in its ecosystem may have driven the development of its formidable jaws and teeth. Additionally, competition with other marine predators could have pushed Ankylorhiza to develop its unique combination of speed and power. While we can't be certain about Ankylorhiza's echolocation capabilities, the development of this sense in cetaceans was a crucial evolutionary step. Modern toothed whales use echolocation for navigation and hunting, and it's possible that early forms of this ability were beginning to emerge in Ankylorhiza's time. The shape and structure of its skull might provide clues about its sensory capabilities, though more research is needed to draw definitive conclusions. The balance between size and agility in marine predators is a delicate one, and Ankylorhiza seems to have struck an effective compromise. Its large size would have allowed it to tackle substantial prey, while its streamlined form and flexible neck maintained the maneuverability needed for successful hunting. This balance would have made Ankylorhiza a formidable predator in its ancient seas. Ankylorhiza's influence on subsequent dolphin evolution cannot be overstated. Many of the features we see in modern dolphins, such as their streamlined bodies and powerful tails, can be traced back to ancestors like Ankylorhiza. While modern dolphins have lost the flexible neck of their ancient relative, they have retained and refined many of its adaptations for efficient swimming and hunting. Ankylorhiza's adaptations made it a formidable predator, but they couldn't protect it from the unstoppable forces of global change. As the late Oligocene epoch dawned, this ancient terror of the seas faced challenges that would test its very existence. The first signs of Ankylorhiza's decline coincided with significant shifts in Earth's climate and oceanic conditions. During the late Oligocene, approximately 25 to 23 million years ago, global climate changes led to alterations in ocean currents and temperatures. These environmental shifts had far-reaching consequences for marine ecosystems, including the habitat of Ankylorhiza. The changing conditions likely impacted the distribution and abundance of prey species, creating a ripple effect throughout the food chain. As ocean temperatures fluctuated, the availability of large-bodied prey that Ankylorhiza relied upon may have become less predictable. This shift in prey populations could have put stress on Ankylorhiza's hunting strategies. The creature's specialized adaptations, once key to its success, may have become less advantageous in the changing marine landscape. The rise of new competing predators also played a role in Ankylorhiza's decline. As environmental conditions changed, other marine species evolved and adapted, potentially outcompeting Ankylorhiza for resources. These new competitors may have been better suited to the shifting ecosystem, putting additional pressure on Ankylorhiza's population. Fossil evidence provides insights into Ankylorhiza's population decline. The creature became less prevalent in the fossil record, leading up to its extinction around 23 million years ago. This gradual decrease in fossil occurrences suggests a slow decline rather than a sudden extinction event. It paints a picture of a species struggling to adapt to changing conditions over an extended period. One theory proposes that climate change and shifting sea levels played a crucial role in Ankylorhiza's extinction. As global temperatures fluctuated, sea levels rose and fell, altering coastlines and reshaping marine habitats. These changes may have fragmented Ankylorhiza's preferred hunting grounds, making it increasingly difficult for the species to find suitable areas to thrive. The combination of changing prey distributions and altered habitats could have created insurmountable challenges for this specialized predator. Another hypothesis focuses on the role of competition in Ankylorhiza's decline. As new predator species evolved and adapted to the changing environment, they may have outcompeted Ankylorhiza for resources. These competitors might have been more adaptable or better suited to the new ecological conditions, gradually pushing Ankylorhiza out of its niche. It serves as a reminder that even the most successful and well-adapted species can fall victim to environmental changes beyond their control. The story of Ankylorhiza's decline offers valuable insights into the delicate balance of ecosystems and the far-reaching impacts of global climate shifts. While Ankylorhiza's reign came to an end, its impact on marine ecosystems didn't vanish with it. What happens when a top predator disappears, and how does nature fill the void? The answers lie in the aftermath of Ankylorhiza's extinction, revealing a fascinating chain of evolutionary events that shaped our modern oceans. The extinction of Ankylorhiza left a significant gap in the marine ecosystem. As an apex predator, it had played a crucial role in maintaining the balance of the food chain. Its disappearance likely led to a period of ecological instability, with populations of its former prey species potentially experiencing rapid growth. This sudden shift in predator-prey dynamics would have rippled through the entire ecosystem, affecting species at all levels of the food web. Nature, however, abhors a vacuum. The ecological niche left by Ankylorhiza didn't remain empty for long. Other marine predators began to adapt and evolve to fill the role of top predator. One of the first to emerge was Squalodon, a genus of primitive toothed whales that shared some characteristics with Ankylorhiza. Later, macro-raptorial sperm whales and orcas would evolve to become the dominant apex predators of the oceans, a position they still hold today. This process of ecological succession is a common phenomenon in nature, where new species or existing ones evolve to occupy vacant niches. The extinction of Ankylorhiza created opportunities for other marine species to diversify and evolve. For example, the ecological niches left vacant by Ankylorhiza and its contemporaries may have contributed to the radiation of modern whale and dolphin species we see today. One of the most significant outcomes of Ankylorhiza's extinction was its influence on the evolution of modern cetaceans. The adaptations that made Ankylorhiza successful didn't disappear with it. Instead, they served as a blueprint for future marine mammal evolution. Many of the features we see in modern dolphins and whales, such as streamlined bodies and powerful tails for efficient swimming, can be traced back to ancestors like Ankylorhiza. The story of Ankylorhiza offers valuable lessons for understanding modern marine ecosystems. It demonstrates the delicate balance that exists in ocean food webs and how the loss of a single species can have far-reaching consequences. This understanding is particularly relevant today as we face unprecedented threats to marine biodiversity due to human activities and climate change. In the field of paleontology, Ankylorhiza continues to play a crucial role. Its well-preserved fossils provide a wealth of information about cetacean evolution and ancient marine ecosystems. Studying Ankylorhiza helps scientists piece together the complex history of life in Earth's oceans and understand the evolutionary processes that shaped modern marine mammals. Comparisons between Ankylorhiza and modern endangered marine species yield interesting insights. While Ankylorhiza's extinction was likely due to natural environmental changes, many of today's marine species face threats primarily from human activities. However, the vulnerability of even such a successful predator as Ankylorhiza to environmental changes serves as a cautionary tale about the fragility of marine ecosystems. The rise and fall of Ankylorhiza illustrate the cyclical nature of evolutionary dominance. Throughout Earth's history, different groups of organisms have risen to prominence, only to be replaced by new, better-adapted species as conditions change. This pattern of succession and adaptation is a fundamental aspect of evolution, driving the incredible diversity of life we see today. The study of Ankylorhiza and its extinction also provides valuable context for understanding current and future changes in marine ecosystems. As our oceans face unprecedented challenges from climate change, overfishing, and pollution, the lessons learned from past extinctions become increasingly relevant. Understanding how marine ecosystems recovered from the loss of key species in the past can inform conservation efforts and predictions about the potential impacts of current biodiversity loss. Ankylorhiza's story offers a fascinating glimpse into the ever-changing nature of life on Earth. This ancient predator's rise and fall remind us that even the most dominant species can succumb to environmental shifts. Understanding extinct creatures like Ankylorhiza is crucial for marine conservation efforts today. It helps us predict how current species might adapt to changing oceans and identify vulnerable populations. As our planet continues to evolve, we may witness the emergence of new apex predators in our oceans. These future hunters could develop unique adaptations to thrive in warming waters or exploit emerging ecological niches. By studying the past, we gain valuable insights into the potential shapes of life to come, highlighting the importance of protecting our marine ecosystems for generations to come.